I am Praful, a PhD student at MIT, and I will be presenting our work, What You Can Learn by Staring at a Blank Wall. Consider a scenario where you are interested in knowing about the number of people or their activity in the hidden scene. From outside the room, all you see is a blank wall inside the room. Looking at the observed wall, it appears to be static to the naked eye, even though people might be moving in the hidden scene. It might appear that this task is impossible, as we do not see any convincing signal, but processing the video reveals extremely small variation, which correlates with the motion in the hidden scene. We can see subtle, imperceptible illumination effects caused by human motion on the wall. While this low-intensity signal is not apparent in the original observation, it can be used to infer information about the hidden scene. In our work, we take as input the video of a blank wall. We extract this subtle, imperceptible signal and perform classification of the number of people and their activity without any scene-specific knowledge. Existing non-line-of-sight methods can be classified as active or passive methods. Active methods interact with the environment using projectors, lasers, Wi-Fi signals, or sound to extract information about the hidden scene. However, interacting with the scene may not be desirable in some applications. These methods often rely on expensive equipment and extensive calibration. In contrast, passive methods take advantage of the knowledge of the scene and the resulting lighting cues to infer about the hidden scene. Having less control over the environment makes the problem challenging. Many methods take advantage of known occluders such as corners or objects in the scene. This introduces structure in the light transport, enabling observation of clean signals corresponding to the hidden scene. But sometimes, knowledge of such occluders and structure is not available. We show that even in such cases, the indirect lighting cues can be used to infer information about the activity in the hidden scene. To understand the indirect lighting cues available in our imaging setup, let us consider a room with two people. The ambient light in the room dominates the observed radiance on the wall. But light takes infinitely many paths before reaching the observed wall. For example, light could bounce off a person, the back wall, or an object before reaching the observed wall, or even be obstructed by a person. These are just some examples of second-order effects. One can imagine light bouncing off different surfaces multiple times before reaching the observed wall. The movement of people in the hidden scene results in change in these subtle, imperceptible illumination effects. To extract this signal of interest, we start by subtracting the temporal mean of the observed video from each frame. The residual is then multiplied by a constant factor to enhance these patterns on the wall for visualization purpose. This amplified video shows the change in the observed pattern as the person moves in the hidden scene. But it is usually dominated by camera noise, resulting in signal-to-noise ratio as low as -35 decibel. To reduce the noise and to summarize the relevant motion features, we average over the height of the amplified video to get a 2D representation of the video, which we refer to as the horizontal spacetime plot. This shows a signal corresponding to the motion along the width of the wall. Similarly, we compute the vertical spacetime plots by averaging over the width of the video to get a signal corresponding to motion along the height of the wall. We use these spacetime plots to train a neural network for two tasks: classifying the number of moving people in the hidden scene and activity recognition. For classifying the number of people, we use the horizontal spacetime plot as it captures the motion features along the width of the wall. We use both horizontal and vertical spacetime plots for activity recognition. Different signatures can be seen in these spacetime plots for the different activities. For classifying the number of people, we use a 5-layer convolutional feature extractor to compute a one-dimensional temporal summary. This temporal summary is pooled over time and fed to a fully connected network for classifying between 0, 1, and 2 people. We use a similar model for activity recognition. Since we have activities which include movement along horizontal and vertical dimensions, we use both horizontal and vertical spacetime plots as input. We have individual convolutional branches to compute the 1D temporal summary for each of the spacetime plots. A small fully connected network then uses the concatenation of these two summaries to predict the activity. The activities include crouching, waving hands, jumping, walking, and no activity. Both models are trained on 12 hours worth of data from 20 different indoor scenes collected in offices, conference rooms, and public spaces. The method was tested over 17-second temporal windows on 5 held-out test scenes. We achieved 94.4% accuracy for classifying the number of people and 93.7% accuracy for the activity recognition task. We also tested shorter windows of 4 and 8 seconds. Inference over these shorter durations led to modest drop in accuracy of our method. Further analysis such as confusion matrices can be found in the paper. In addition to the offline testing, we packaged our capture and prediction system into a portable setup for real-time deployment. Here is our imaging setup in an unseen room. The camera observes the blank wall while a person moves in the hidden scene. The real-time system shows the observed wall, the amplified video, and optionally a ground truth video. The corresponding spacetime plots are shown along with real-time class predictions using our trained model. The ground truth video is recorded and visualized just for visual reference and would be unavailable during an actual deployment. This is the real-time demo for the activity recognition with the same layout. We visualize both horizontal and vertical spacetime plots, which are input to the model. The system detects the walking, and now, as the person crouches, the system is quick to change the prediction. Even though our model was trained on indoor scenes, our real-time system also works in unseen outdoor scenes for both tasks. Note that in this particular test scene, there was no wall between the observing camera and the hidden scene, but the camera only observed the blank wall. This real-time application runs on a consumer laptop, performing acquisition of the data, pre-processing of the video to spacetime plots, inference, and visualization. We have tested this system in multiple indoor and outdoor scenes and observed comparable results. Here we present the activity recognition task in an outdoor setup. Note that this setting is somewhat favorable to our method, as the person is wearing clothes that have high contrast against the background and is walking close to the wall. This results in clean signal in the spacetime plot. To better understand the effect of such parameters, we formulated an idealized model of the setup to derive a formula for the signal-to-noise ratio. The SNR is inversely proportional to distance, but proportional to the ambient lighting and the relative contrast between the background and the subject. The derivation can be found in the paper. To validate the theoretical trend, we recorded the SNR as a subject performed the 4 activities at different distances with 3 different lighting intensities. We find that the empirical SNR follows the slope predicted by our theoretical model. The small deviations can be attributed to higher order lighting bounces in an indoor scene, which is not accounted in our theoretical model. Aside from the signal quality, the relative motion of 2 people can also impact the performance of our method. For example, 2 people walking together in lockstep might be indistinguishable from just one person. To study the impact of different motion patterns, we rendered a synthetic dataset using an idealized 2D flatland setup illustrated here. The two persons move in a sinusoidal pattern with controlled amplitude, phase, and frequency. Our model trained with real data works well on these synthetic samples. Based on the performance of our model on the synthetic dataset, we find that large relative amplitude is preferred. Having contrast between the motions is more valuable than simply having large motions. Out-of-phase motion is preferred as the signal can be mistaken for a one-person scenario when the two people are always moving in the same direction. In our work, we explored an extreme scenario for passive non-line-of-sight imaging with minimal scene-specific knowledge. In particular, we don't make any assumptions about scene geometry, such as occluders or pinholes. Yet, we show that it is possible to use even this noisy, unstructured signal to perform meaningful inference about the hidden scene. Thank you.